2019, Tesla made a move to acquire a San Diego company called Maxwell Technologies. The main driving force behind this acquisition was a technology called the dry battery electrode, or DBE. Now, there have been plenty of great videos by pretty great YouTubers going over the economic benefits of this technology. But to my knowledge, there really hasn't been too much talk about the real nitty-gritty scientific details on why this technology works and how this technology works and how this process works. And that's really the purpose of our video today. So first, let me shout out Trucks V2. They have it's this guy right here. They have a really great clothing brand. I really recommend you guys check it out. I'll have a link in the comments section below. And I want to thank all and welcome everyone who's new to the channel and who subscribed in the recent days and weeks. We're going to take a slight detour from the series that we've been going through on Lindens' handbook of batteries, because I think it's a really important video to make at this time. And I want to thank everyone who left feedback on the previous videos. I really take it to heart, and as a reminder, I welcome any comments, criticism, critiques, and counter-arguments in the comment section below, using my secretive methods. Scarlett, do you have it? Come on.
Relax. Got it.
I have found Maxwell's patents in their dry battery electrode technology. Now, this is important because it lays out the fundamental scientific reasoning behind their technology, how they created it, and why it works. I printed it out right here, and I'm going to show you screenshots on the screen. So we're going to go into these patents. There's one in particular that I think summarizes it the best. And I think this is more than pretty much any other channel has done. So we're going to use this patent as a guide. And obviously, I'm going to link in the description below if you'd like to follow along. But before we go into discussing really patents, we have to just have a discussion on intellectual property. So the most common type of intellectual property are patents. And it's mostly because they're public information. They're public, anybody can reach it, anybody can grab it. So what is a patent? It's essentially a claim over a certain type of idea or process that prevents other people from using it. It's essentially a paper, this one written here, that exerts a claim over a certain type of idea or process, and it's written to try to convince the government that this is your idea and convince the government on how it's different from the state of the art and how this is the new state of the art and everything else is the prior art. The other major type of intellectual property is trade secret. So if you are wanting of an example of a type of trade secret, think of the Krabby Patty formula. It's something that is material vital to your business that sets you apart from competitors, but you want to keep it secret. Generally, it's a manufacturing process or a material combination that you really don't want your competition finding out about. It's not something you can easily reverse engineer, because otherwise it wouldn't be a secret for long. I had a professor who taught manufacturing engineering as well as engineering ethics at the college I go to. His name is Dixon Davis. He's an absolute legend. Great guy. Love him. He has decades of experience in the industry, and he would be randomly taking calls from NHTSA in the middle of class, and stuff like that. Crazy stuff. Awesome guy. He told me that one trade secret is worth about 1,000 patents. So my point is that there may be some aspects to the patent that we're going to be going over that have slightly changed, and Maxwell has kept a secret, so maybe it's a slightly different version of the process that may have changed over time. So when we find out truly what this technology is from Tesla themselves, it may be a little different in the final version. But this is basically where they started with and how they came to this concept and what the science behind this concept is. So some things might have changed, but this is probably the best look inside their mindset and when they had one created into this technology. So without further ado, let's finally get into this patent. The title of the one that I'll be using as a reference is going to be Battery with the Recyclable Dry Particle-Based Electrode. And it's invented by Lindens, Porter Mitchell, and another person who I can't pronounce because I'm bad at pronouncing names. And it was patented by Maxwell Technologies. The patent was filed in 2012 and was published in 2013. And it was really one of the most recent in the string of patents that I was able to find. There's several different patents on this technology. This is one of the most recent and one of the kind of best ones that I was able to find, the best explainer. A lot of the other ones, earlier ones, were basically built into this. So portions of the older ones were incorporated as this one as like the fundamental framework for it. So there's some overlap between it. And it really starts with the beginning portion of it, really focusing pretty heavily on ultracapacitors. And that's because Maxwell was an ultracapacitor company. That was their main driving revenue, and that was really what their process was. But there are some problems with ultracapacitors. The major problem with ultracapacitors is that they're expensive, they have a low energy density, both volumetrically and mass-based, and that can cause some problems. So if you're trying to store a lot of energy in it, it's difficult compared to a lithium-ion battery, and especially over longer cycles or longer times. It lasts longer cycles, but there's basically, it's similar to a battery, but it's designed for a better power density and worse energy density. And they really haven't taken off the same way lithium-ion batteries have, and they believed that changing the manufacturing process would be the key to doing this. And so that's where they came in, is they first examined, how do we make ultracapacitors? How do we make these double-layer capacitors? Well, they're made generally two ways that they're made. They're made by coating, which is the same way that you make a battery, and they're made by and the other version is extrusion. So coating is the traditional process that batteries are made from, and that involves taking an active material in carbon and combining it with binders they're like a polymer, and mixing it with a liquid additive. The additive reacts with the binder and it dissolves it, but the additive overall is just not good for the performance of the cell. So they try to bake it off and they try to get rid of it, and when they bake it off, the binder re-dries again, and that's how you get the battery electrode component as a whole. It's that dried portion of it. But that's why you have to try to bake it off, and that's why you put it in an oven. Then after you put it, in the coating process, you'll put it in the oven after you put it on, and you adhere it to a current collector, which, depending on whether you're making the anode or the cathode, it's some different materials, sometimes aluminum, sometimes copper, stuff like that. The other process is known as an extrusion. And so in the first process, you make what's called a slurry with the chemical combination. It's very much a liquid form, and it's very runny. Well, in the extrusion process, instead of making it so it's more of a liquid, you make it so it's more of like a dough. And then what you do is you extrude it, or you basically pull it through an extrusion machine. And as you're pulling it through, there's this process called fibrillization that occurs. So what is fibrillization? Well, it's basically the process of you take fibrils, or just really fine fibers, and you turn it into a matrix, or you turn it into basically a mesh. And that's how you create the electrode film. So what does that mean basically? Basically, you extrude it, you put pressure, you put stress on it, and that causes the state to change in the material. And then after you do that, you calender it, which you basically take it through rollers, and you reduce the thickness to what size you want it to be. Now, in both cases, you have to attach the electrode to the current collector, and you do that by adding a liquid additive with another adhesive, and then attaching the two parts together, which helps with electrical contact. Now, Maxwell engineers found and identified that there was fundamentally one massive major issue with the technology that we currently use to build ultracapacitors and batteries. The additive itself. Now, once you add it, no matter how hard you try, you cannot get rid of the additive. They would go in to test it to see if they could. They would bake it for days at a time, and they would still find measurable traces of the additive in the electrode material. Now, the additive is really bad, one, because it's toxic, two, because it hurts the performance of the cell. The additive reacts with the active material in the electrode. The additive reacts with the active material in the electrolyte. And because of that, it reduces the performance of the cell. And it's not good. That's why you have to try to bake it out. It's because it reacts with all these things. So the more concentration you have, the less reliable the cell is. The earlier the cell will break down. But the problem is you can't completely break it out. You can bake it, a lot of it out, but not all of it. And even when you do, this toxic additive gets evaporated into the air, and now the air is toxic. So what do? You got to try to filter out the air. Well, there's this really complicated process people have figured out, and I'm going to show you a picture of it on the screen from Lindens handbook of batteries. And what it's going to show, they're essentially trying to recycle and recover some of the additive after use. But obviously, this whole system is increasing cost, and all of this crazy stuff stems from the additive itself. So the idea was, if we can remove this additive, we can, just by chain of reaction, just by an analysis of first principles, if we can remove this additive from the process, we will do all of these positive things and reduce cost heavily. And then we can manufacture ultracapacitors on a greater scale. You know, I haven't even mentioned that all these ovens and all this process slows down production capacity, reduces it, makes it more difficult to produce the same cells at the same time. And that's what they figured out, and that's why it's significant. And what they realized is it's not only something you can use for capacitors, it's something that you can also use because the coating process is the same when you're manufacturing a capacitor, with just some different materials, as when you're making a battery. They realized that it could be used on the same thing after they built it. So what is this technology? How did they figure out on how to replace the additive? Well, according to this patent, they lay out a couple of different ways they can do this. Process is basically the same for the cathode, which is the positive side of the cell. We talked about that last episode. And the anode, which was going to be this episode, but we're going to talk about it next one, which is the negative side of the cell. So we're going to focus mainly on the cathode, as that's 22% of the cost of the lithium ion cell. And we're going to kind of follow through that process and see what ends up happening. So this right here is an image of the process for the cathode. So as you can see, up at the top portion of this picture, they mix a metal oxide with a conductive carbon and with a binder PTF. So the metal oxide, that's like the lithium metal oxide, so that'd be something like the NMC, the NCA, the LMO, all the different types of lithium metal oxides that you can jam into the cell. That's the positive half of the cell and the positive active material in the cell. You mix that with the conductive carbon and with the PTFE, which PTFE stands for polytetrafluoroethylene, and it's basically a synthetic polymer. One of the most notable types that they specifically list is Teflon. So they're basically putting Teflon in there and mixing it up. So the binder that they're including is totally dry. And it's important to recognize that the patent also mentions a couple other different types of dry polymers as well. For example, polypropylene, polyethylene, copolymers, and blends of different polymers. So this is one of those examples that I talked about of trade secrets, where now over time we may end up seeing a different type of polymer being used in the end product. And so that's important to recognize as a whole. Hey, this is going to be maybe a little different in the end result, but essentially just think about it. You're adding a polymer in as the binder. So what you do is you take those three material types and you mix them together. You don't add any additives, because that's the whole purpose of this whole concept of technology. So you don't get any dough and you don't get a slurry. You basically just have a dry mixture of particles. And the patent calls for mixing them for around 1 to 10 minutes in what's called a V blender. But notes that time can change based on the batch size. So maybe if you have a bigger batch, it's going to change the amount of mixing time. So that has to be adjusted for optimization of the manufacturing process. The next step is called fibrillization. So like before, the goal is to reform the binder into a film around the activated carbon and activated materials. And they accomplish this by pulverizing the mixture, so the shear stress causes the binder to fibrilize. So as before, we talked about how it went through an extrusion, and that's what fibrillized it. In this process, what they use is actually a jet mill. This clip is going to explain pretty well, I think, how a jet mill works.
The benefits of the jet mill are many. We're able to grind materials without any contamination. We're able to grind materials without any heat generation. And we're able to grind materials extremely fine, finer than any other dry method available. Jet mills will grind friable or brittle materials or crystalline materials to the 1/3 to 15 micron particle size range. We manufacture jet mills in 11 different sizes. The internal components can be stainless steel, they can be tool steel, they can be of ceramic, tungsten carbide, polyurethane, Teflon. Jet mills are also known as fluid energy mills. So the power source can be nitrogen, it can be air, it can be carbon dioxide. The material is injected into the jet mill. In our case, it goes into the first chamber, which is a distribution chamber. It is evenly distributed and goes through multiple ports in front of the grinding jets. The material goes to the grinding chamber, it goes out into orbit. It stays in orbit and collides with other particles of the same material. As soon as they're fine enough, they migrate towards the center of the mill, climb over a weir, and they're air classified as they come out. Each mill requires a different flow of motive gas. The smaller the mill, the smaller the airflow. The larger the mill, the higher the airflow and the higher the throughput.
But essentially you're shooting air into and causing that to mix it around and grind it down. So now after you use it, if you zoom in 100,000 times, you really can't see very much evidence of the fibrils. But they're there and their effect is there. And the wonderful thing is that this eliminates additives completely. You don't have to add any additives in from this process in order to make and assemble the electrode film. But there is one concern that we have with specifically the jet mill, and that is it uses compressed air. And compressed air, when you compress it, you have an issue with water forming, condensation forming, and so you don't want that. So you have to kind of dehumidify the air before sucking it up into the compressor and then spraying it. So that is one added cost that you have to deal with. And you have to make sure that the water level is the right. Otherwise, that could end up impacting the life cycle of the battery because you're adding in water, and your whole goal is to make it as dry as possible. Once again, this patent covers its bases by listing the other ways that they may be able to achieve these steps. So one of the ones is by pin milling, another impact pulverization, roll milling, and hammer milling. And these are all just different things to exert different types of stress on the material that still accomplish the same option of fibrillization. So since 2012, they might have found something that was more cost effective than the jet version, but they were able to effectively use that in the early version. So everything is going to stem off that. So like I said before, in the polymer, it's going to be a little bit different probably in the final version, but that's what they used initially. And it's the same concept of what you're doing. You're basically exerting a lot of stress that breaks down the binder, and then on a molecular level, they bond together. So you can assume that it's going to be the same thing for the most part. The patent also mentions that mixing and the fibrillization process might be able to be combined into one, so that'll further drop costs. So instead of mixing and then switching it to this, you'll just be doing it all in one batch and then pumping it out. That'll depend on whether or not a couple different factors. You have some issues with certain things that you probably have to work out, but if you can do that, that might further drive down costs, especially at scale. And after that, you bond the film and to the current collector. So you bond the electrode film to the current collector, and then you put together the rest of the cell. You put on the line and you assemble the jelly roll cell or any type of other cell, actually. So I think after explaining, because that's how the manufacturing process essentially works, that's really it. It's nothing super crazy. I want to talk about the performance benefits of using this process as opposed to the additive-based one. And to do that, I'm going to show you this picture here. So give me 1 second. I'm going to pull it up on my page, my printed copy. So it's going to be up on the screen. So the first one I'm going to show you, figure 2E in this patent. Now this is additive-based carbon particles, and what you can see all around it is the dissolved binder. So what happens is when you add a slurry to the mixture, when you turn it into a slurry, because of what's called capillary action, the binder that's dissolved will actually completely wrap around the electrode material. So as you can see, it's completely circled around that material. And then when you dry it, it hardens and binds everything together. Now, this is significant because now let's go ahead and look at the dry particles. So we're going to look down and look at the dry carbon particles. That's with using this technology. And as you can see, it's a little more clumpy. The binders are less evenly distributed. They're more clumped together. And so if you're just looking at the picture, what do you think looks better? Generally, the thing that probably looks better is that kind of the old version looks better. But performance-wise, you don't want that. So as we discussed before, the binders are a polymer, which means they're basically like a plastic, and they're not very good at conducting electricity. The whole point of these carbon particles is to conduct electricity. So if you're putting a layer of this basically polymer plastic material in between these two particles, you're essentially drastically increasing the resistance between these two particles. You have something that's designed to have a low resistance, you have something with a high resistance, and you have a low resistance. You do that, you're generating extra heat, and you're basically just screwing, it's not an efficient way to go. Why is it really significant to have these two guys contacting? And why is it significant to lower the overall electrode resistance in the cell? Let's go back and look at the fundamental laws of electrical engineering. So first thing, Ohm's law. Ohm's law states that voltage is equal to amperage, or basically the current, times the resistance. So if you reduce the resistance, but you maintain the same voltage, the amount of amps that can go through it goes up. The power law when it comes to electrical engineering is that if you keep voltage the same and you increase current, you're increasing the power of the cell, which means that both on the discharge level and on the charge level of the battery, you're able to put through more power. Power is energy per second. You can put more energy in the same amount of time, or the same amount of energy in less time. What does that mean? That means let's look at the example of a vehicle, electric vehicle. Charging times drastically less. The energy that you're able to put to the road drastically more because of this technology. It has less resistance, so you're going to have better time conducting energy through the cell. And not only that, is because you have less resistance, you're now going to have less heat generated by the cell, which means even less resistance, faster charging times, more stable battery cells, more stable electrolyte because the electrolyte's not getting heated up. All these crazy things are all stemming from this one technological change. And because of that, you have a way better cell as a whole. And that's just that. You get rid of the additive. That increases the longevity of the cell. That means you're going to have a cell that lasts longer. So let's go down the list. More power, more energy storage, faster energy storage, more power down on the road, more speed, no additives, no drying times, drastically less on cost, drastically less on all of these lines. Improvement just by changing this one technology and by examining something through a first principles approach. So, and I haven't even mentioned the first part that I mentioned when I read the beginning of this patent. These batteries are recyclable. Now, it may not be end of state recycling. So it may not be you run it for 1 million miles or however many cycles you're going to run it through, and then you take it to the Tesla dealership and they recycle it. It may not be that. But we're talking about, so it's not end state recycling. We're talking about manufacturing recycling. So let's say you're doing an original battery cell and you mix a little too much in and the slurry is just a little bit too runny, and you put together the cell and you run it and you test it. Shoot, it doesn't work anymore. I messed it up. Well, what do you have to do? You have to throw it away. It's toxic. You have all this toxic material in it. What are you supposed to do? All this toxic material, you can't just get rid of it. You have to treat it as toxic waste. Oh no, that had a bunch of cobalt in it. We're now throwing away a bunch of super expensive cobalt. If this whole batch is bad, what are we supposed to do? We put cobalt in there. That's super expensive. We're now throwing away this super expensive, hard to get material. So, but the cool thing is with this process as outlined, and this may have changed, but by the time of this patent, they basically went through ways that you can break it apart after it already forms, reform it into the original materials, throw it in there again, and be able to pull out the same material. So there's a couple different processes they laid out that all worked basically on the small scale. This may not work as well on the large scale, but at the very least, we're at least going to have less waste product coming out the back end of when you're manufacturing these battery cells. And that's great. That's going to reduce costs. That's going to reduce the amount of material usage. So this technology was so amazing. Are there any potential downsides to it? Well, traditionally there may be some additives that get mixed in from the formation of like the lithium metal oxide or a couple stuff like that. So you have to watch out for that now. So you now have to go in and we have to change the way we manufacture certain other parts of the battery in order to further improve this technology and really realize it to its full potential. But that's hardly a downside. That's really just a change in the process that kind of has to go through. So we just have to be more careful about that. And then according to this patent, from what I understand, the current collector still has to be baked in order for the adhesive to activate. So there still would have to be some baking going on. So there still have to be some ovens. It doesn't completely eliminate ovens altogether because there has to be an additive added to the current collector. But who knows? Since then, they might have figured out a way to improve that as well and to reduce that as well. So what are some of the big impacts this change has? Well, it opens about 1 million doors. So every type of chemistry that they've tried on this again, and they've come back to using this, improves its overall capabilities using this technology. So what does that mean? That means now when we're looking at it, we got to go back and check every technology that didn't work when we're trying to make this new breakthrough chemistry and see if this new breakthrough chemistry actually works with this process. See if it can actually improve the performance and actually make it commerciable. So we're going to probably see a pretty big uptick in papers written about this different types of technology combinations spinning off of this technology from Tesla. from Maxwell, now owned by Tesla. Another thing is because there may be the additive might react with the active material that causes the cell to be less stable when you're trying to make it, which means that we may be able to find new active material that now cost, or that actually can work better than we thought it would before. And because you don't have an additive, it's going to work better now. So we can try, there's a bunch of things that we can try now that we thought didn't work. Maybe it works now because it's a totally new manufacturing process and changes certain characteristics of the material. And so there's even more potential opportunities, but they themselves, or Maxwell themselves, have stated that they've tried MCM 811 and 111, NCA, LFP-LTO, sulfur carbon, and silicon composite. Like I said, it works on both the cathode and the anode. And all these are pretty hefty improvements from what we can understand of just from our charts that they've released so far. A lot of it's under wraps though, so we really don't know a lot of the information. But from what they state, they have hit and demonstrated greater than 300 watt hours per kilogram of specific energy. Why is that important? Well, greater than 300 watt hours per kilogram is absolutely massive. So as mentioned before, it's believed that Tesla's to be around 250 watt hours per kilogram. We're talking about jumping that up all the way to 300 watt hours per kilogram. That is a massive change. And it's not even just, it doesn't even just say equal to 300 watt hours. It's greater than. We don't know exactly how greater than. We don't know how exactly commerciable this greater than is. But it's very possible we're going to have something in the next few years that is greater than 300 watt hours per kilogram in vehicles. And that's really, really absolutely revolutionary. And that's going to, we'll see it effectively in range pretty significantly. So to summarize, by implementing this technology, we're about to see a massive wave of growth out of Tesla in the next few years, both in production size as well as in the chemistry side of things, and as well as monetarily, because not only does this technology work in lithium-ion batteries, but it works in capacitors. Not only does it work in the secondary version of lithium-ion batteries, which means the reusable versions, but in like single-use batteries, so like Duracells, it works in those too. So it's not just that, but it also works in the building of electrodes of fuel cell vehicles, so fuel cell storage systems. It works with that too, so they can license their technology to everyone. Duracell, you get some, all these people can be licensing them out, and Tesla could just be over here collecting the bread. So now this technology doesn't really mean anything in relative to solid state electrolytes or solid state batteries as a whole. But because of this advancement, and because it's very likely that Tesla will be now managing their own development cycles, the amount of money and they're going to bring in from their vehicles through this process is going to be massive. Which means that they could then spend a lot of that money on R&D, and we're about to have an explosion of new technology stemming from this innovation. Because now we have to go through and we have to try all these things again. We may figure out better batteries in the coming years. And that's actually really, really exciting. So if you want to continue on studying batteries with me, I'm going through Lindens' Handbook of Batteries. It's really a great read on it's pretty up to date on a lot of stuff and a lot of battery technology. So if you guys are interested in following through that with me, feel free to subscribe and leave a like, because this is very interesting. So I'm a student, so school's starting up again for me. So it's going to be pretty busy in the next few months. So it may take a little bit longer for me to get out a video, but just know we're going to continue in on our series. I do want to cover whenever Tesla's Battery Investor Day. I'm probably going to try to do a live streaming it, and then doing a reaction to it right afterwards. Something along those lines. We'll see. If that's something you're interested in, go ahead and leave a comment. Or alternatively, if Tesla wants to invite me to their Battery Investor Day, I'd love to go do that too. But yeah, so that's the basic premise of the scientific reasoning on why we're going to see a pretty hefty advancement in Maxwell or not in just Maxwell, but in Tesla's batteries in the next few years. That's the scientific reasoning. So feel free to comment if you guys got any questions or comments. Thank you all very much. Have a great day.